All right, let's just jump right in. When you think about geology, it feels like one of the most, well, solid sciences out there, doesn't it? It's all about the ground beneath our feet, something we can literally touch and map and measure. But what if I told you that for all its confidence, geology is actually hiding some of the biggest mysteries in science?
I mean, on the surface, geology seems to have it all figured out. We've got a name for every single rock, from granite to schist. We can draw these incredibly detailed maps of fault lines and mineral deposits. We can look at a landscape and pretty confidently predict the patterns of erosion that shaped it. It all just feels so certain.
But here's the thing, that confidence, it's a bit of a mask, because for every single process that geology can explain, there's a fundamental origin or a trigger it just can't quite get a handle on. It gets the how, but the why and the when, well, those are often total blanks. So let's start with the absolute basics, the very engine that drives our entire planet. We're talking about those massive continent-sized plates that are constantly shifting around, creating mountains and oceans as they go. And this is the foundational mystery right here. We can measure the speed of the Pacific plate moving northwest, no problem. We totally understand the mechanics of subduction zones, where one giant plate dives right under another. But we have no definitive answer for why Earth's crust decided to break into all these pieces and start this global conveyor belt billions of years ago. So what we're left with is a bunch of really compelling but totally unproven ideas. Was the early Earth just so incredibly hot that its crust was kind of doomed to crack under all that strain? Or did our vast oceans act like a lubricant, weakening the rock and allowing it to break apart? Or was it all just some cosmic accident, a complete fluke that made our planet so unique? We've got our working theory, but absolutely no birth story. And if you think that's a head-scratcher, it gets even weirder when we look right next door to our planetary twin, Venus. Think about Venus for a second. It's almost the exact same size as Earth, it's made of all the same stuff, and yet its surface is one single solid piece, what scientists call a stagnant lid, that traps a mind-boggling amount of heat. It has no tectonic plates. So why? Why did one twin become so dynamic and geologically alive, creating the perfect conditions for life, while the other basically became a static pressure cooker? It's one of the biggest questions in all of planetary science. And this uncertainty about our planet's engine, it's not just some academic puzzle. It has very real and frankly sometimes terrifying implications for us living up here on the surface. We're talking about chaotic forces we still can't really predict. Let me just throw a number at you. 600 kilometers. That's almost 375 miles straight down. That is the staggering depth where some earthquakes actually happen. Just let that sink in. Because way down there, the pressure is so immense. We're talking hundreds of thousands of times the pressure you feel at sea level, that rocks shouldn't be brittle. They shouldn't be able to fracture or snap. Basic physics tells us they should deform and flow, more like putty or really thick clay. And yet, they do. They shatter with enough force to send seismic waves rumbling across the entire planet. This is a huge paradox. Now, of course, we've got theories. Maybe it's sudden mineral transformations or trapped water making things brittle, but none of them explain all of the deep earthquakes. The honest answer is, we just don't know for sure. This same unsettling lack of certainty carries right over to volcanoes. The popular image, the one you see in all the diagrams, is this huge cavern just filled with sloshing, liquid-hot magma waiting to erupt. But the reality? It's so much more complicated and way less understood. The truth is, a magma chamber is less like a lake and a lot more like a slushy. It's a mush of mostly solid crystals with the molten rock just filling in the gaps. And it's not one big chamber, but this complex network of smaller pockets that are only sometimes connected. This messy reality is exactly why we still can't answer the most critical question. What's the exact trigger that tells this mush, okay, it's time to erupt? So when you start putting all these pieces together, from the birth of tectonics to the weird behavior of magma, you start to get a totally new picture of geology. It stops being about having all the answers and starts being about respectfully mapping the very boundaries of our own ignorance. We draw these beautiful, color-coded diagrams of the Earth's interior, crust, mantle, core. But we have to remember, those are just models. They're really elegant guesses based on how seismic waves bend and bounce their way through the planet. We've never drilled to the mantle. We have never, ever seen it. The vast majority of our world is, and probably always will be, completely invisible to us.
And this brings us to this brilliant insight, one that's often credited to the physicist Richard Feynman, that just perfectly captures the state of the science. Geology is fantastic at understanding the processes, the middle part of the story. It's the beginnings and the endings that are still totally wrapped in mystery.
Let's think of geology as studying a river. We can be absolute experts on that river. We can measure its current, we can map every single twist and turn, and we can build excellent models to predict how it's going to erode its banks next year. But what we can't do is go back in time and find the exact spot where the very first drop of rain fell that started it all. And we can't know for sure where its very last drop will evaporate when it finally runs dry. So, what's the ultimate takeaway from all this? It's this. After all the mapping and all the measuring and all the modeling, the single biggest mystery is still there. It's not just about how our world works, but why our world is the way it is. Why did this specific combination of heat and water and rock produce a dynamic, living planet with a churning engine instead of a static, overheated Venus or a cold, dead Mars? That right there, that is the question at the very heart of the unseen Earth.